Welcome to the satellite communication course. So today we will learn that a beam switching here. Now in the beam switching, so this is nothing but a tracking technique. And in this tracking technique, that antenna generates a two pattern that are symmetrically above and below the bore side there. Now this one is about a satellite direction. And for this, we supposed to be consider that this one is about a track axis. Now these are the two pattern for this beam A and beam B. And this one is about a satellite direction. If we say that V1 is greater than the V2, means what? The bore side of that satellite direction is, or you can say that this one is about a bore side, means which direction there. So means that satellite direction is above the bore side, then we can say that V1 is greater than the V2 there. Means you can say that voltage received by pattern 1 that will be larger than the pattern 2. Now another case, if that satellite direction, if it is below the bore side, then what will happen? Then V1 will be smaller. You can say that above bore side. Okay. So likewise, what we can say that a V1 is equal to V2. If you can say that V1 is V2, then you can say that, okay, right. So we can say that bore side here. So that is about a below bore side. This one is a above bore side. So according to this V1 and V2, so that difference we can say that if V1 minus V2 is a positive, then you can say that above bore side, and V1 minus V2 if it is a negative, then it will be the satellite direction that will be below the bore side there. So that difference is nothing but what? The offset angle axis with this satellite direction. So that is about, we can say that these two beams, so whichever we are getting by these two pattern, and these two beams are used tracking the satellite direction there. If we receive the signal from the satellite, then that case we need to measure the voltages and then we can find the error there. And according to that error voltage, then we can find out what will be the a position of that a satellite, and then we can adjust that azimuth and elevation. Means that error will gives us the what will be the azimuth and elevation there. Next we see that a conical scanning. So in the case of a conical scanning, we supposed to be consider that a satellite is transmitting. This one is about a earth station. So we need to see that what will be the satellite axis, satellite axis here. Okay, this one is about a satellite axis, and then we need to see that what will be the radiation pattern of this whatever the signal we are supposed to. So now this one is about a beam axis. This one is the beam axis. This one is about a satellite axis. So in the case of a conical scanning, so that antenna is to be rotated around its axis. Okay, means we can say that we have the given antenna. It is to be rotating likewise. Means we need to rotate the antenna with the given axis. Okay, that antenna is to be rotated around its axis with a small squint angle. With a small squint angle. So then, according to the given rotation, so supposed to we can say that this is about a satellite axis, this is about a beam axis, and we're supposed to say that this one is nothing but a rotation axis now. Now that beam is to be rotated. This is about your beam. So beam is to be rotated. So that is about a beam rotation. And then we have the main beam axis there. And this one is about a rotation axis. So antenna is to be rotated with a small squint angle. And this one is called as a squint angle. Means antenna is rotated around its axis with a small squint angle. So then whichever the signal received, so according to that we can adjust the position of the satellite. Means that beacon signal is to be transmitted from the satellite. Then beacon signal that is to be received. If that received signal, whichever we are getting, in that case, if that modulation is a zero, then we can say that the axis is aligned with this satellite. Now here in the conical scanning, that antenna is rotating, or this particular antenna is to be rotating, and this according to that we will get the received signal. So that is nothing but a rotation is to be takes place using the auto rotation there. So that's called as a auto tracking of this a satellite there. So antenna beam is rotated at actual by rotating the antenna, and that actual antenna is to be rotating, or either we have the feed or a subreflector is to be rotating if it is a large antenna. So that will get that a conical beam scanning. So this one is just like a scanning the axis of this radiation pattern. If supposed to be that beam is here, so in that case we'll receive the full signal there. If that antenna beam supposed to be likewise here, instead of this beam axis is coinciding to the satellite axis, so in that case we'll get that a maximum radiation. Okay, we receive the maximum signal there. So that's why we can say that a rotation of that antenna or a rotation of that particular subreflector, since according to that, so the tracking can be done. And in this particular tracking signal, a modulation is introduced that is called as the amplitude modulation, and that amplitude modulation for the received signal. And if whichever the received signal we are saying it is modulated, and that modulation, if it is a zero, then we can say that that antenna axis is coincides there. So that is about a conical scanning. Then next is about a step tracking. In the case of a step tracking, that motors are used. You can say that we have a stepper motor, that is about, and the stepper motor are present on this the position of this antenna here. We have the satellite there. So these are the various motors to be used. You can say that a stepper motor here, and that these stepper motor are used to verify the decision. That decision is regarding what we have the elevation there, or we can say that azimuth control. These are about the elevation control to the stepper motor, or a azimuth control to the stepper motor. You can say that a decision circuit. So we are receiving the signal from the antenna. That is, we require a no low noise amplifier. We receive the signal. Then we convert the signal down converter. Then envelope detector. Okay. Now this one is about envelope detector, and according to that, decision circuit will provide the input of elevation control, or a, we can say that a azimuth control there. Okay. Now in this case, so that antenna is to be moved using this stepper motor. So we move the antenna in a what? In a small steps. We move the antenna in a small step. So according to that, we can adjust this azimuth and elevation. Once we adjust that azimuth and elevation of this earth station antenna, then we can adjust the whatever the satellite axis of this through this antenna there. Okay, that is about your azimuth and elevation there. So now a satellite sends some particular signal, that is about, you can say, downlink signal. Okay, so we will receive the signal, and that signal strength we receive with a different position of that antenna, and then each and every position of that received signal that will be received by this antenna, that will be compared after each and every steps there. And according to that, we will get that particular step that will provide we, or that gives the error, and according to that we can find out that what will be the position of this earth station there. Means two signals we are receiving, means two successive signals we are receiving. We will verify their difference, and that difference gives us the error voltage. So according to that difference voltage, we can fix the position of this earth station using this elevation control and a azimuth control there. So if we receive that signal, that will be a stronger one, higher. In that case, no need to change the position. And if that strength of the signal is less there, then we need to use the stepper motor to fix the position of the satellite, that earth station. So that's about just like a simple strip tracking. So we have a signal strength received by this low noise amplifier through this antenna there, then it will be down converted, then envelope detector is there, and then we have a decision circuit. So that decision circuit will check the whatever the strength of the two signals. So according to that, then according to that difference, if it is higher or lower, so according to that we can find out the, or we can appropriately generate that elevation or a azimuth position there. Okay, so means using this stepper motor, so elevation and azimuth is to be adjusted according to the, whatever the decision circuit provide the input to this. Now that is about just like we are measuring the signal strength, means a signal to noise ratio for this two signals. Another example is about, we can say that a electronic beam splinting. So it is just like a method of generating the two different beams. So generally we say that we have the antenna, and this is nothing but we can say that a beam here, beam 1, and then we supposed to be consider that there's another beam here, supposed to be consider that another beam. Okay, likewise there are the beams, various beams. So this one is about a foresight of an antenna. So this one is about a satellite position. Now this one we can say that for this given beam we have the angle alpha. From this we'll have the different angle here. So means main axis is likewise. This one is about a main axis. And for this particular main axis, we can see that here a satellite position is to be varying. Likewise, we have this key in here. And then if it, if there is a small variation in the position, that is the theta here, and that theta is to be obtained here. So means here we have the multiple antenna, and that multiple antenna will generate a squinted beams, and that is about a multiple beams are generated. Okay, likewise there are about beam 1, beam 2, beam 3, likewise, and this one is about a main satellite antenna. So we have, there is a small deviation in the a beam here, and that because of that particular small deviation in the beam, so we can adjust the position of the satellite. So here the beam squinting means what? We have two different beams, and that two different beams having the squint angle of a, we can say that alpha, which is beam 1 supposed to be say, and with respect to this bore site of an antenna. This is about a bore site of a antenna there, or angle of from the bore site here. So here we can the satellite position. So from this to this, that is about a squint angle alpha from the bore site of the antenna. So the bore sight is deflected from the satellite axis, supposed to be it is by an angle theta. The strength signal of this beacon signal received from the satellite by this two beam, that will be supposed to be considered that a G1 and a G2 for two different beam. Then in that case, we can find out what will be the signal loss at an angle theta away from the bore side. So that will be, we can say that if supposed to be considered that from this to this, okay, this is about your beam here, and this one, a main beam coincides here at this particular point, likewise. So now that we need to find out that the strength of that beacon signal, we have these two beams, we say G1 and G2, and for this we need to find out that what will be the gain loss, and that gain loss is to be calculated for this G1 is equal to 12 of, if it is a parabolic reflector, then G1 is equal to theta by theta 3 dB. And that theta 3 dB is nothing but what? A half power beam width. This one is about a half power beam width of the antenna. And that half power beam width generally for the parabolic reflector, it is approximately 75 by lambda by T. That is in a degrees there. Here we can say that T is equal to diameter of an antenna. And then the gain loss at an angle, that is a squint angle alpha, from this bore side, it will be G1 is equal to what? 12 of theta minus alpha divided by theta 3 dB, and is G2 is equal to what? 12 of theta plus alpha by theta 3 dB. We'll get that a G1 and G2, and difference between that dz delta z is, so we can say that G2 minus G1 is equal to what? 12 of theta square 3 dB. Okay, I think I forgot this one. Okay, 12 by theta square 3 dB in bracket of theta plus alpha bracket square minus theta minus alpha bracket. So that is about a delta g. And after solving that, we'll get that delta g is equal to 48 theta alpha, that squint angle, and that theta of a 3 dB square. Or you can say that a small deflection angle, that is about a theta, from this satellite axis position, that will be what? Delta g into theta 3 dB square by 48 of a lambda. Sorry, 48 of a alpha, not lambda. Okay, that is about your that theta, that is a small error in the position, that is about a theta. We have the G1 and G2 for this, and then we will find out a squint angle, that is about the alpha here between the position, beam position. So we can say that G1 and G2 for this, gain 1 and gain 2 for this both side of an antenna. So here a main beam here, small deflection there, so that's why G1 and G2 we can calculate here. So that is about a tracking, and that we need to find out that delta G. So theta is to be a minimum. If the theta is minimum, then we can say that, or theta is zero. So there is no variation in the position of the satellite bore side of an antenna. Okay. Then another example is about a smoothed strip tracking. We have just earlier we have seen that there is a strip tracking here. Okay, this one is about strip tracking that we have seen. In smooth strip tracking, whatever the prediction data is there, that predicted data is to be given to the strip tracking input, and then we can, according to that, we can achieve the smooth tracking there. So in that case, we need to know about that what will be the satellite position, or we can say that orbital position of the satellite that is to be predicted. According to that, a disturbances occurs in a given particular period of a time. Then that, according to that particular prediction and strip tracking, we can adjust the position of the antenna with respect to the elevation and a azimuth there. So this is just like a tracking algorithm, and that is to be predicting the values of the orbital position of the satellite, and as well as the strip tracking is to be used in the smooth strip tracking. Then we have seen that another is about a simultaneous lobing. So in the case of a simultaneous lobing, so we have the multiple beams are generated. So we supposed to be consider that we have the four horn antenna. Likewise, we say that we have the four horn antennas are there, and that four horn antennas, they will generate the beam, or we can say that a multiple antennas, they will generate a multiple beam, and that multiple antenna will receive the signal, and then that will they will compare, and according to that we can find out the error there. So that is about a simultaneous lobing, and according to that error, so then we need to compare whichever the signal received in terms of amplitude and a phase, and according to that we can adjust that azimuth and a phase there. So simple comparison of this particular four antenna is there. So we need to receive the signal from a various multiple beams. Suppose we can consider that summation of what antenna A, B, C, and D. And for this elevation, we need to find out A plus B minus C plus D. Or for the azimuth, variation in the small to delta azimuth. Okay, in that case, we need to use that A minus B plus C minus D. So means multiple beam antennas to be used to find out the whatever the position there. So antenna A, B, C, and this antenna A and B here, whichever the this one is about the adder here, this one is a plus plus, will get that A plus B signal. Okay, so we can say that this one we have A minus B, that B input, that is about minus, this one is about a plus here, A minus B here output. Similarly, we have a C plus D. We can say that this one is about plus, this one is a plus. We'll get that a C plus D output here. And then we have the This one is about a plus. This one is a more minus. We'll get that a C minus G out. Okay, likewise. So from this, we can calculate that a difference between that or sum of all these component there, whichever the reference signal received by this ABC. So we have A plus B now. We're supposed to be add this A plus B and this C plus D. So we'll get that output, that is summation of what A plus B plus C plus D. Likewise. Okay. So now we can say that we need to find out the elevation, small variation in the delta. So A plus B minus C plus D. So this is about A plus B minus C plus D. So this one is about A plus B here, and this is about a C plus D. Okay, we'll get the output, that is the elevation likewise. And then another is about what, a output of what, A minus B, that is A minus B plus we have a C minus D, both will be plus. We'll get that a azimuth there. Delta azimuth is equal to what, A minus B plus C minus D. Okay, that is about the azimuth we can calculate. So this way we can consider that we have the ABCD. We need to find out a sum of all the beams from this A and B, and that will give the sum signal, and that sum signal will be act as a reference signal in the receiver operation. The difference of the signals from ABCD, that will give us the error signal in the, we can say that difference of A plus B and C minus D, that will give the error, and that error signal in the elevation here, and that azimuth here, the difference of the signals AC and BD, that will give us the azimuth there. And these are the signals that are used by the receiver to drive the motor or control the motor in the direction of that antenna azimuth and elevation there. So that is about, we can say that a simultaneous looping, or we can generate that a particular signal or in the simultaneous looping. So we use a monopole tracking method, and that monopole tracking method can be employed using this multiple antenna beam. So how, what will be the a monopulse receiver? So in the case of a monopulse receiver, if you see that, so we have the sum of the input. You can say that RF amplifier, then it will be a down converter mixer, then we have the IF AGC amplifier, then we have the amplitude detector, we have a AGC here, input to this, then to the IF AGC here, then we have the IF, AGC, amplifier, IF, AGC, amplifier. Then so we have the down converter mixer. And here we are giving the output to this RF amplifier. This one is about the azimuth and what will be the variation in that azimuth there, or we have the elevation delta. Okay, elevation delta, elevation azimuth there. That is the input to this IF, and all these are local oscillator. Okay, so this one is about oscillator here. Then after that, here is the phase detector. So it will generate that azimuth error. Then we have phase detector, so it will generate the elevation error. So means from the amplitude detector, we have input to the phase detector, so that it will generate that azimuth error as well as the elevation error. It's just like a tracking. If we have this SM and these two signals that are amplified and down converted to an IFAGC here, IFAGC amplifier, and that is IFAGC means what? Automatic gain control here, IF amplifier. The some signal output that will be detected and that will be used to control the gain of all the three IF amplifier. Okay, so that is about, you can say that this one is a control here. Gain will be controlled by this. By likewise. Okay, this one we have the IF amplifier. And this automatic gain control AGC that will remove the effects of the propagation medium in the variation in the particular signal level. So that is about some signal again provide the reference to this IF AGC so that that will give a reference signal to the phase detector there. So now we can see that here is some signal now IFAGC, then it will give the reference to this phase detector here, and that will provide a tracking the difference in this azimuth or azimuth error or the elevation error there. And that error, whatever we are getting, that difference or that particular error, that will be given to the whatever the motors, and according to that, azimuth and elevation is to be corrected there. So that is about your various antenna tracking systems that we have seen. So we have seen that a antenna tracking system, that antenna tracking system in which we have learned that there are the a program tracking, manual tracking, program tracking, and auto tracking. In a manual tracking, that operator provide the data to track the antenna position, azimuth position, and the elevation position there. In a program tracking, the data is input is given and that data is to be varying according to the durations and all. That is about a program tracking. And then a auto tracking, so in which we learn that a sequential loading in simultaneous loading. Then we have learned that a simultaneous loading and a sequential loading. And then we have learned a auto tracking there. And then we have learned that how that azimuth and elevation is to be varied there. So that is about your antenna tracking for the earth station receiver. And next we'll see that what will be the various amplifier use.